Welcome to this educational presentation on high-tech polymers in the modern world. My name is Daniel Howard, and before we go on to discuss high-tech polymers, we're first going to address the questions: what is a polymer and how do we make one? Here we have ethene. Now a polymer is a large molecule made up of repeating units of small units called monomers. Ethene can be called our monomer, so when we join lots of ethene molecules together we produce this. Note the repeating unit. The ways in which we synthesize polymers is either by chain growth polymerization or step growth polymerization. In chain growth polymerization, we add alkene monomers to the end of a growing chain, so our previous example with ethene was an example of a chain growth polymerization. Free radical, cationic and anionic are types of mechanisms for synthesis in chain growth polymerization. Step growth polymerization involves reacting monomers with two reactive functional groups together and removing a small molecule, like so. So now that we understand the raw basics behind polymers, we can now go on to look at the high-tech polymers that have shaped and are currently shaping our high technological world. So we're going to start off with a little bit of history. In 2000, these three men were awarded the Nobel Prize for the discovery and the development of conductive polymers. So what makes their research so interesting? Now, to answer that question, we must first look at what gives these polymers their properties. Now, most organic polymers are electrical insulators. They don't conduct electricity, but most conductive polymers are organic. So how can this be? Well, to illustrate what I'm about to explain, here we have polyethene. Now, conductive polymers are made up of an extended conjugated backbone, and here we have polyethene's conjugated backbone, and we can see it consists of carbon-to-carbon double bonds and carbon-to-carbon single bonds, which alternate. The significance of this is that we now have overlapping p orbitals, like so. The importance of this p orbital overlapping is that the electrons within the p orbitals become delocalized. That is, they are now free to move within the polymer. Aromatic rings such as benzene are another good example of a conjugative system and are a common group found in conductive polymers. However, when a conductive polymer is first synthesized, they are not very conducting. An additional process needs to be done, and this is called doping. Doping greatly increases the electronic conductivity. There are two ways a conductive polymer can be doped, and that is by N-doping when an electron is added, or P-doping when an electron is removed. This generates charge carriers which can move in an electric field. They can move through the polymer like so. Organic light-emitting diode, OLED, a thin film light-emitting diode in which the emissive layer is an organic compound. The relevance to conductive polymers is that it relies on the property of some organic conductive polymers to electroluminesce when a voltage is applied to them. They are sometimes referred to as PLEDs, polymer light-emitting diodes. They eliminate the need for a backlight and are paving the way for flat panel displays. PPV derivatives are commonly used in OLED technology. These derivatives have different functional side chains which control the colour that is produced. In the future, we will probably see more OLED devices, and this is due to their useful properties such as low power consumption, which makes them perfect for battery-powered devices. OLED screens are already on the market, and one example is the AMOLED screen in Samsung's Galaxy S, and Sony is incorporating a 5-inch OLED screen into the upcoming next-generation gaming portable device. We also may have the pleasure of seeing flexible OLED screens, and this opens up a ton of untapped possibilities. Other applications of conductive polymers include solar panels and batteries. Lithium-ion batteries have revolutionized our electrical equipment, and lithium-ion polymer batteries, where the conductive polymer can act as an electrode, have evolved from this. In conjunction with solar panels, these technologies will be fighting the battle for future greener and more renewable energy sources. Car manufacturers such as Hyundai have already started researching lithium-ion polymer batteries for use in hybrid electric cars. So I think it's a safe bet to say that we'll probably see more of this technology on the road in the future. We've already mentioned lithium-ion polymer batteries, where one of the electrodes can sometimes be a conductive polymer, but the main important thing about a lithium-ion polymer battery is that the electrolyte is a polymer, such as PEO. Polyethylene oxide is an example of a polyether, and is formed from the monomers ethylene glycol and ethylene oxide. The mechanism for synthesis can either be cationic or anionic depending on the catalyst. To illustrate cationic polymerization, here we have isobutylene. We first initiate our starting material with an initiator. In PEO, polyethylene glycol is our starting material. E indicates any electrophile. What we get formed is a cation, which can then react with another monomer, forming another cation, and so forth, and overall we end up forming a polymer chain. Anionic polymerization is quite similar, but instead we form an anion. Nu indicates any nucleophile, and note the strong electron withdrawing group, which is essential, as we are adding electrons to already electron-dense regions. For the synthesis of PEO, anionic polymerization is usually more favoured. This is because in anionic polymerization, the polymer chains grow smoothly at the same average rate, so we can predict and control the synthesis of our polymers, leading to low polydispersity values. When we refer to polydispersity, we are talking about the mass distribution of a polymer. A low polydispersity means that all the polymers are roughly the same size, that is, there is a narrow distribution of masses. Lithium polymer batteries evolved from lithium-ion batteries, and these are completely different from one another and not to be confused. One fault of lithium-ion batteries is this. Lithium polymer batteries avoid this mostly because the polymer electrolyte is not flammable. Other useful properties include the ability to be specifically shaped to fit a device, and this is due to the lack of battery cell casing. This is a great benefit for manufacturers, as devices come in all shapes and sizes, and the lack of battery cell casing also makes the battery lighter, and this is perfect for handheld devices. So where is the future of polymer battery technology heading? Well, Japanese scientists at Waseda University have produced a flexible paper-like battery. It is an organic radical battery where the radicals are added to a thin polymer film, which is only a couple of nanometers in thickness, and is capable of super fast charging. What you've seen and heard is only a selection of the polymers shaping our modern high-tech world today. It is important to note that polymers are everywhere, even right down to the circuits which drive our electronic devices.
This world, it's yours to carry on where you lie. There's nothing stopping you tonight. Breathe the air, decide to live your life. It's yours to